Hi everyone. So for this part of the talk, I'm going to make and try to defend a rather bold claim, which is all of the cool stuff we've heard so far, proof of work, mining games, mining pools, proof of stake, that all of these are really interesting and important problems, but they're a small subset of all of the incentive issues that arise in cryptocurrencies that we could be working on. So I want to try to tell you about what are some of the interesting problems out there that we're not looking at very seriously so far, and why that's an opportunity. So that's why this talk is titled From Praxis to Theory. But to be clear, I'm not a practitioner. I'm not a theorist either. I sit a little bit closer to practitioners. I come from the security and privacy community. I've been working on cryptocurrencies for about 5 or 6 years now. Just as one quick pointer, I led a Princeton team that created a textbook and an online course on cryptocurrencies if you're interested in checking that out. Okay, so I'm going to split this into 2 parts. One, I'm going to make a series of observations based on what's happening in practice that we're, I think, not modeling so much because there aren't very easy, convenient ways to model them theoretically. And I'll suggest some ways in which we could start modeling them to have somewhat more realistic models of mining and other incentive issues in cryptocurrencies. And the second part is more about smart contracts. It's about blockchains as platforms for mechanism design. And smart contracts, I think, and I think a lot of people think, are the most exciting idea in cryptocurrencies. It's a major reason why Ethereum exists. And what I want to argue here, that smart contracts, they are mechanisms, of course, but they're not simply mechanisms that happen to execute on top of blockchains. They have interesting and important differences from other types of mechanisms, and therefore it leads to new problems, new models, and we need to do new theory. And I'll give you some examples of what some of these interesting differences are, and hopefully that can spur some nice concrete models that we can use to analyze these smart contracts. So let's get started. Let's start with some observations of what's happening that's not so convenient to model theoretically. And the first thing I want to highlight is incorporating non-strategic players within game theoretic models of mining behavior. Yeah, players who might not necessarily act to maximize their mining revenues, etc. And I think the reason this is important to model, if we look at the history of research on cryptocurrencies, most of it, in fact, has used models that are not based on game theory at all, and instead come from the consensus and Byzantine fault tolerance literature, where there's a very different kind of model for how players behave. And in fact, this comes from looking not so much at human agents or economic agents, but nodes in a distributed system. So the consensus literature originated at solving problems like, what if you have 100,000 nodes in a data center, for example, that Facebook or Google might be using? What's happening in the situation is that these thousands of nodes together are operating as one virtual computer. However, some of these nodes might be faulty, some of them might crash, some of them might behave arbitrarily, and we want to be able to assert that under certain assumptions, the so-called consensus protocol works correctly, and this distributed system is going to function as we expect, as one single virtual computer. So that was the origin of these models. And in the distributed systems literature, the rationale for these 3 groups, the so-called honest nodes that follow the protocol, are supposed to be nodes or computers where the software is working as intended, it has not been corrupted, it has not been hacked, for example. And then you might have nodes that are suffering a network problem and therefore might go offline, might not communicate with the rest of the nodes. And interestingly, the reason why there is the so-called Byzantine node in this type of model is not so much because that node might actually behave arbitrarily, but because it captures our uncertainty over how to model such a node. And this has in fact happened in practice, even if we go all the way back to some of the cases where these models were used by NASA, for example, to analyze the distributed systems or redundant systems that were used for space flight. It turns out that some of the wiring errors that occurred in those systems were just so hard to actually think about ahead of time and model correctly that it turned out to be really useful to assume that this is somehow going to behave in a worst case way. It's behaving as if there is an intelligent adversary that is trying to cause the consensus protocol to fail. So that's the backstory for how these models came about. And then the computer security community adapted these models a little bit to consider situations where, for example, you divide a cryptographic key among 5 people who jointly control a company, and then some of them are in fact honest, some of them might go offline due to network problems, and there might in fact be an adversary who bribes 2 of them and asks them to do malicious things, arbitrarily bad things, in order to corrupt the security of the joint computation. So that's the history of these types of models. And when Satoshi created Bitcoin, my guess is, looking at the history, he looked around for the types of security arguments that could be adapted to arguing about the consensus protocol in Bitcoin, and this type of model proved to be very suitable. So a Satoshi-style proof would go something like this. Assume that the majority of players in your system are honest and the rest are malicious. And of course, in cryptocurrencies, when we say the majority, we mean that it's weighted by hash rate or whatever the resource in your system is. In other words, the majority of hash power in your system is controlled by these so-called honest players who, under any circumstance, will follow the protocol as specified. They don't have any incentives. They're not trying to maximize revenues. They're constrained to behave in this way. And then the proof might say something like the probability of a consensus failure that lasts more than k blocks is exponentially low in k. So this is very similar to the random walk argument in the original Bitcoin white paper. Yeah. And even today, most of the work on security in cryptocurrencies is happening outside AGT and uses models and proofs of this nature. There is, in fact, no argument about incentives. And that is something that has bugged me a little bit, and that's why I started working with Matt, and that's why I'm happy to be here. And I think there needs to be a meeting of these 2 worlds, and that is the first thing that I wanted to share with you. So of course, just to recap, the default view in AGT is that all players are strategic, and to the extent that anybody is honest, it's not because it's a characteristic of the player, but simply that it's a strategy that they choose to adopt at a certain time because it happens to be incentive compatible. This notion of a Byzantine adversary, though, that's a little bit harder to model in AGT. I think it requires some sort of universal quantification over a large universe of strategies. And an example of a game theory style statement might be that as long as no player has more than some large fraction of the total hash power, we might hope to prove that it's a Nash equilibrium to follow the protocol. Now, if we can prove a lot of statements like this, then I think we would be in very good shape, because these 2 sets of assumptions, even though they come from very different backgrounds, would end up saying roughly the same thing. The consensus style proof would say, as long as there's no single adversary that together controls some large fraction of the hash power, then things are going to turn out OK, and the game theory style statements are going to say something like this. But I don't think that we're quite there yet. We have some proofs so far in the game theory style. We don't have something that we're really happy and satisfied with, even for simple consensus protocols. But I think the main questions in terms of unifying these 2 views a little bit, I don't think we're going to completely accomplish that, but a little bit, is to be able to say, how do the predictions made from these 2 sets of assumptions compare with each other? How are they similar? What are the discrepancies between them? Can we look for some sort of hybrid models where, for example, we start from a game theory view, and then we add in these honest and Byzantine players and see what happens under those scenarios? And here's what might be exciting. Consider the following type of statement. Suppose we're able to say that compared to all players being strategic, that is the default AGT view, if you add in an epsilon fraction, an arbitrarily small fraction of players who are either honest or malicious or both, then that situation results in a very different equilibrium. If we can prove something like that, I would find that very exciting because it suggests that even an arbitrarily small number of players not being strategic could dramatically alter the consensus guarantees of a cryptocurrency. And this is the kind of possibility that I think we should seriously explore. Question?
Why not looking just at the trembling handle of Nash? Basically the same idea?
I think it's yes, it's definitely trembling hand equilibrium would be related, and Matt, feel free to pitch in. The thing that I don't know is how you would model the idea of a malicious player. I don't know if that would be covered by that. Yeah, let's take it offline. Yeah.
So I wonder if you've considered analogies to like statistical ensembles, where when you want to have a result, you kind of use a variety of tests. And I think it would be really nice if we could have like the same protocol analyzing a variety of both security and systems and game theoretic.
Completely agree. Yes, that would be really nice to have. Yeah.
Have you considered also a hybrid model where you kind of start from the Byzantine fault tolerance side and you say, oh, look, not all Byzantine faults are really can cause a change in the client software.
Yeah.
Maybe we can narrow down the space of strategies.
That makes sense as well. Thank you.
But that is like an undesirable thing.
Well, this would be interesting. Desirable or not, I don't know, but I think we should explore if this kind of thing is possible. This would be surprising to me, is mainly what I'm saying.
Those examples as engaged in classical generative.
That's good to know. Thank you. So I'll offer a couple of reasons why I want to emphasize that we should look beyond the really straightforward AGT view, which is that at least number one is, at least I think, that selfish mining and attacks based on pools, a lot of interesting deviant strategies have been proposed in the academic literature so far, but I don't think of any of these as having been observed in practice in a way that's been independently confirmed. There have been rumors of selfish mining attacks on some altcoins. Matt mentioned some of these, but based on the reports I've seen so far, I don't know how much to trust them. And it doesn't look like miners so far are adopting a lot of these interesting deviant strategies in the literature. I want to get a better understanding of why that is. To what extent are miners actually strategic? To what extent do they have the control over their mining infrastructures to be messing around with mining strategy? And if not, we should really start taking account of that in our models. Of course, there have been various things like double spending attacks that have been observed, denial of service attacks, etc., but not some of these more interesting theoretical strategies. One other quick point I want to make that I hope we might be able to get into in the panel is that there are what I would consider, and chatting with Matt would also consider to be important theoretical flaws in Ethereum, for example. There's one called the verifier's dilemma, which has to do with the incentives for verifying the computation of smart contracts. That we consider to be pretty important, but from what I understand, practitioners in the Ethereum community consider it to be, at worst, a minor annoyance. So I would like to get a better understanding of what is the reason for this difference in perspectives. And so those are some cautionary notes. I want to say that the AGT view doesn't directly translate to what we see in practice. Okay. Another thing I want to point out is that the game is much broader than mining. We've talked about the mining game, but there are a variety of things that interact with the mining game that I think are also important to model. One is protocol upgrades, because we're good at analyzing a mining game when the rules of the game stay the same. But what about the Calvin ball situation when the rules of the game are themselves being adapted? And that actually happens in practice. In Bitcoin, there was the SegWit protocol upgrade about a year ago that happened after a very contentious several-year-long process. And Bitcoin is very conservative with respect to protocol upgrades. This was the only major one in a while. But there are other cryptocurrencies, including Zcash and Ethereum, which consider regular protocol upgrades to be part of a healthy functioning of a cryptocurrency. And so that becomes, I think, an important situation to model. Similarly, in theoretical work, we assume that forks are bad things. That is, forks where two different branches emerge and go on indefinitely. Essentially, the cryptocurrency itself splits into two, and you might have the history is never going to reconcile with each other for these two branches of the fork. We assume that this is a bad thing, and we try to bound the probability of this sort of thing happening. But in practice, life continues after a fork. It's not the end of the world. We've had situations where a cryptocurrency split into two, and when you look at the exchange rate of the two daughter cryptocurrencies, or whatever you want to call them, the total market capitalization increased at that moment. So value was created. And so in that sense, the fork was even a very positive thing, right? And again, there are some cryptocurrencies that consider regular forks to be just part of what happens in normal operation. So that's, again, something that I think we're not very good at modeling.
It's not clear whether those forks can be sustained for
all the time. We can't keep on printing new cryptocurrencies and have the market cap go up.
Absolutely, which is another reason I think we should model them so that we can get a better understanding of how much of this can you sustain and what are the incentives that go into the creation of a fork, which is kind of what I want to talk about next. I want to go into the technical details a little bit of what forks might look like. Actually, let's start with protocol upgrades. Here's what a protocol upgrade might look like. So over there on the left, you have the white blocks before the fork, and before the protocol upgrade. And the gray blocks represent some of the nodes, some of the miners who have upgraded to the new version of the protocol, which is incompatible with the old one. And they start creating their own branch because it's incompatible, and it quickly becomes the longest branch. But some nodes, some miners, are still on the old version of the protocol. And so they're occasionally creating blocks as well, but those blocks are just these short branches, these one-block orphans. They never turn into a chain of their own. Yeah. So this is one situation that might happen. And what this is a soft fork upgrade. And in a soft fork upgrade, the new blocks are valid under the old rules. So when you have this gray chain here, all of the miners are trying to mine on top of this one, except that when a miner who has not upgraded mines a block over here, that's going to be ignored by the miners who have upgraded because the old blocks are not valid under the new rules. Yeah, so there's an asymmetry here. So this is called a soft fork. And if you can pull this off, if you can manage to pull this off, that's a very good situation because a soft fork will succeed as soon as a majority of the hash power in the network switches to the new rules. So Bitcoin's SegWit fork a year ago was an example of a soft fork, and it was relatively easy to pull off just from a technical perspective. The other kind of protocol upgrade that you might have is this sort of situation. It's a hard fork upgrade where the rules have changed in such a way that not only are the new blocks invalid under the old rules, the old blocks are also invalid under the new rules. So this is symmetric now. And so as long as there are some miners who have not upgraded to the newer version of the protocol, they're going to be off doing their own thing in their own branch. Yeah, so this is a hard fork protocol upgrade. Notice that the boundary, the difference between a protocol upgrade and what I'm calling a fork is actually not that clear here. So let's look at that in more detail. What is actually the difference? Now, if your protocol upgrade looks like this, what you've created here is you've created two different cryptocurrencies, whether you intended to or not, because the history is going to diverge between these two branches. And as long as there is any miner that is stuck on the old branch, that branch is going to continue indefinitely. And as long as there is anybody who is willing to accept a currency that exists in the old branch, that still exists as a cryptocurrency. So the cryptocurrency forks in this situation. So protocol upgrades can lead to forks of the cryptocurrency. And in fact, there's no strong technical difference between what we call a protocol upgrade and what we call a fork. It's mostly kind of a moral difference based on the motivations of where people are coming from and what they're trying to achieve with it. Yeah. So I think this is why it's really important to study forks, because both protocol upgrades and forks are very common in a lot of cryptocurrencies. It's not the end of the world. Life goes on. In fact, you might create two different cryptocurrencies, and that might lead to an increase in the total market capitalization some of the time. So I'll quickly mention, these are a few examples of famous forks that have occurred over the last few years, and you can kind of put them on a spectrum. Some forks or some protocol upgrades are about noticing a bug in an old version of a protocol and then fixing it, and then there's no controversy about that. Everybody adopts the new version. On the other hand, you might have another kind of uncontroversial situation where there are two groups that have different visions for the future of the cryptocurrency. So they just amicably decide that they're going to have different versions of the protocol, and the cryptocurrency forks into two, and nobody's fighting with each other. You genuinely have two different cryptocurrencies. But in the middle, you might have an interesting situation where the two groups are fighting for legitimacy. Each one of them might say that they're the real Bitcoin. They might say that they're the ones that are actually following in Satoshi's vision. And then you have this really interesting situation here where there's game theory involved in figuring out how this fight for legitimacy is going to turn out. Which of these cryptocurrencies is going to gain more adherence and is going to be more used, and whose price is going to appreciate with respect to the other. And so I think this is a really interesting and important game that is happening all the time. Forks are happening all the time in cryptocurrencies these days. And we're not modeling that very much. And the reason that that's tricky to model is that we have to look at the actions of a number of different types of stakeholders in the system, not just the miners. And that becomes a very tricky thing to do. But it is important to model them, I think, because a healthy cryptocurrency does need all of these types of entities. So you can ask, how do fights for legitimacy play out? And how should we structure a cryptocurrency so that we might have one kind of outcome or another? Is there a role for so-called social consensus, which Vitalik and others have proposed as a way of dealing with these forks, which is the members of the community, including the developers and service providers and exchanges and so on, will decide that one branch of the fork is legitimate and the other one is not, so we should all follow this one. So can we actually model what happens during that process, and is that a legitimate way to resolve some of these forks in cryptocurrencies? Okay, so a third way in which I think there are some nuances in modeling what's going on with mining is that costs and payoffs are complex. And let me give you several examples of this. The first one is that in-game actions affect the exchange rate. So what do I mean by this? You will often hear from cryptocurrency practitioners, oh, you have this fancy attack that a miner can deploy. It might be true in theory, but they're never going to do that in practice, because they know that if they do, then news of this attack will cause the value of the cryptocurrency to tank, and therefore their holdings in the cryptocurrency, Bitcoin, Ethereum, whatever it is, will be worth much less, and so they're actually just shooting themselves in the foot, and that's the practical reason why these attacks won't happen. It's an argument you hear all the time. It's actually a very difficult one to refute because there's not a lot of practical data on this, but it's also not clear how to model this theoretically. And it is, in fact, true that in practice, miners are also speculators. And what I mean by that is that most miners, in practice, have a long position on the cryptocurrency that they're mining. When they get mining rewards, they don't immediately liquidate that and turn it into USD or whatever. They hold on to it for long periods of time. And so there is a lot of weight to this criticism that carrying out an attack can affect the exchange rate and might they might end up shooting themselves in the foot. And that's what I'm saying here. But when we do look at the few situations where this has happened in practice, things are not so clear. I think just very recently, last month or so, there was a 51% attack against an altcoin called Verge. And here's what happened when this attack was discovered. In the week following the attack, the price actually increased 30%. And also, they announced a deal where they would be becoming a payment option for this porn site, and so thereby greatly increasing in prominence. So apparently, no news is bad news here, and so news of the attack was actually great news for this cryptocurrency. And so, we see that this argument we hear all the time, at least in this instance, didn't actually work. So I think we need to have some rigorous thinking about this. How do these kind of in-game actions affect the broader game? How do they affect the exchange rate and others? Yes?
One of the problems with these arguments from like a point of view of like designing these protocols is that they apply to all of the protocols, no matter how insecure and crappy they are, and in the same way. And so like they don't really, it's not really an argument that we shouldn't improve our protocols. It's an argument that favors every protocol in a non-discriminatory fashion. And therefore, I'm not really sure it's useful for protocol design.
I see. That's a good point. Thank you. Yeah.
So about both this and the non-strategic players, I guess, wouldn't this be something that kind of goes away as the market becomes more efficient if we assume that cryptocurrencies are going to reach $1 trillion valuations and we're going to have really sophisticated players kind of dominating the space?
That's a good question. It is possible that once the market becomes more efficient, miners will have to become more strategic. And in fact, there is an argument you could make today that so far mining has been just a kind of a really dumb way to speculate on cryptocurrencies. And most of the reason that miners have been profitable is simply because cryptocurrencies have been going up in value so dramatically. And we could argue that once those dramatic fluctuations stop happening, as one assumes they eventually will, then miners have to become strategic or drop out of the game. So that might be true. This one I'm not so sure. It's possible that even in some future equilibrium state, in-game actions will affect the exchange rate.
So you can also make opposite argument. First, like the cost of mining tax does not necessarily scale up with the value of the cryptocurrency or the market cap. Second, if you have efficient markets, you can short cryptocurrencies too. And once you short the cryptocurrency, the tax is actually profitable if the valuation goes down.
But if markets
are the
are
same thing as being not the opposite.
Yeah, exactly. Because if markets are efficient, you can only do that a finite number of times before arbing all the profit out. And
but like
then the response, the price, the exchange rate reaction should be unpredictable. Otherwise, there's arbitrage opportunities.
No, like there's currency attacks.
Okay.
So there's also the cost of it.
All right, let's take that offline. I'm happy to jump into that after this, but let me give you a couple of other reasons why miners' costs and payoffs are complex, and we're not fully modeling them yet. One of my favorite ones is that often one of the payoffs of mining is an evasion of capital controls. What do I mean by this? In China, imagine a miner doing the usual mining thing. They're investing in their mining infrastructure in Chinese currency, but they're making rewards in Bitcoin or some other cryptocurrency, which they can easily convert to US dollars. So one of the ways they benefit from mining is being able to convert RMB to USD in a way that's not easily detectable. And so that is a kind of payoff that we don't usually model when we think about the mining game, and we also don't think about flat rate electricity deals, for example. A miner has to be in it for the next 2 years because of an electricity deal that they made and that sort of thing. All right, so I started 10 minutes late. Should I take 10 minutes to do this part, or should I stop here? What do people think? Give me some suggestions. Yeah, take 10 minutes to talk about this? Okay, cool. So this is a part that I'm really excited about. I want to argue that smart contracts are mechanisms with some interesting differences from traditional mechanisms, and we need to tweak our theory in order to be able to handle them. And so let me give you 3 examples of this. The first one that I want to give you is the idea of an honest Ponzi scheme. And this is one of my favorite kinds of smart contracts. There are lots of honest Ponzi schemes operating on Ethereum. There was a paper that looked at them recently, and I found, and I think it found close to 200 or so of these honest Ponzi schemes. So what does that mean? How can there be an honest Ponzi scheme? It's very simple. Recall that in a Ponzi scheme, there are different types. Let's look at a Queuebased Ponzi scheme. Let's say that it promises a 50% return on investment. So here's how that works. Matt might invest with me. I'm running the Ponzi scheme, an amount of $10. So what I'll do is I'll take his money and I'll put him in a queue. He's the first person in a queue. And then somebody else, let's say Alex, pays me $5 to participate in the Ponzi scheme. I'll put him as well in the queue and pay those $5 back to Matt. And I'll keep paying Matt. When Matt has received $15, because I promised a 50% return, then I'll remove Matt from the queue, and then the next person in the queue will start making money. Yeah? So that's a Ponzi scheme. Now, the critical thing to observe here is that all of the behavior that I described for myself can be done purely algorithmically. You don't need any human judgment to do it. And in particular, you can write a smart contract to do everything that the operator of the Ponzi scheme would do. The cool thing about this is that the smart contract is running on Ethereum. Anybody can examine the code of the smart contract. They can verify for themselves that it's doing exactly this and nothing less and nothing more. And they can verify that the creator of the smart contract is not going to run away with the money. And that's why it's called an honest Ponzi scheme. Right? Of course, it doesn't prevent the risk that nobody's going to invest after you, and so you're going to be stuck holding the bag. There's no way to prevent that. But at least it prevents the risk that the Ponzi scheme is going to be an exit scam. The creator is going to run away with all of the money. Yeah? And notice that in a smart contract, the smart contract itself is an agent. It owns the money. The creator of the smart contract does not own the money. So unless there's a provision specifically coded into the smart contract, there is no way for them to actually abscond with the money. And so that promise is actually true if the code is not buggy and it's correctly written and if you can verify it. And so these things have been really popular. Lots of people have been playing these games. But the reason I want to share this with you is that it's a simple example of what you can do if you have this ability to make and enforce a commitment. This is something you could do in real life if the operator of the Ponzi scheme had some way to make a commitment and for them to be held accountable to that. Yes, so the honest Ponzi scheme is a fun thing, but what are other interesting, important things you can do now that smart contracts give us a really easy way to do commitments? In other words, algorithmic agents can't lie, and that's part of where smart contracts get their power. However, they also have limits compared to humans and institutions who might be agents. So I want to, my next two examples are going to be about the limitations of smart contracts compared to human agents. And so the first of those is the idea of decentralized name markets. So what is this? So first of all, a centralized name market, a good example is DNS. It's run by ICANN, the Organization for Domain Names and Numbers. And they run a market where you can go buy domain names from them. And then after that, there's a secondary market you can also trade with your peers. Yeah? And these names are domain names, and you can associate IP addresses with those names. And that's how the web works. That's how the domain name system of the web works. So that's a centralized name market. And there have been many attempts to create decentralized name markets on top of blockchain platforms. And the claim that I'm making is that the market design for these name markets in a decentralized setting is far harder than it is in a centralized setting and leads to some interesting pitfalls. So I want to try to justify this point. So first of all, let's see how this kind of market would work in a decentralized setting. It would work based on a smart contract. And again, a smart contract is an algorithmic agent. It's an agent whose actions are specified in code and fixed and cannot be changed once they've been programmed in. So this is the smart contract. It executes this name market functionality. The way it works is that Alice, as a user, wants to register a domain name. She pays a certain fee to the agent in order to register it. And what the agent does, it has a massive table that's actually stored in the blockchain, in this decentralized data structure that's stored on these thousands of nodes that registers her name and the IP address or whatever that she puts in it. Yeah, and then this is a public data structure. Anybody, Bob or anyone else, can simply look this up. That's the whole concept. We know that the agent's actions are fixed. Nobody controls it. And so this is actually a really simple way to realize a DNS-like system without any central authority like ICANN. So intuitively, it sounds believable that this is possible. So this is a thing that's working today. You can go run this in your browser now if you install the right browser extension. There's an altcoin called Namecoin that does exactly this. It was actually the first fork ever of Bitcoin. It's existed since 2011. And so this browser extension, what it'll do is if it sees a .bit domain name in your browser, instead of asking ICANN, the DNS system, for the IP address, it will go and look on the decentralized Namecoin blockchain. It will retrieve the IP address from there. And this was very popular back in the days, if you remember the SOPA and PIPA scare, because people thought that this was a way to do domain names without a centralized authority being able to block you. And it's part of a much broader vision that I won't really go into. But here's the AGT part of this. Here's why it's actually hard to do this, and here's why Namecoin is actually not doing a very good job of this. In a single word, it's because of squatting. So what is the squatting problem? Here's what I mean by squatting. Squatting is the idea that somebody might go and buy up a lot of domain names because they're valuable property, hoping to profit from them later. And that might happen for three reasons. One reason is that in a decentralized setting, there's no trademark enforcement. There's nothing preventing me from going and purchasing bankofamerica.bit. I can't do that with the actual domain name system because trademark enforcement exists for that system. You can't have that in a blockchain platform. Also, it might happen because this algorithmic agent doesn't know what the market price is for some domain name and therefore might underprice it. And similar to scalping, somebody might buy up all of the underpriced domain names hoping to resell them for a profit later. Also, and here, this last one is my favorite one. We actually, when we analyzed Namecoin, we found that a lot of names were squatted because a lot of people were hoping that not only would the value of that individual domain name increase in the future, they were hoping that Namecoin itself would become much more popular in the future. and therefore they were buying up domain names as a way of speculating on the platform itself. And so for that reason as well, they bought up a lot of domain names. Again, it's somehow not a problem that arises so much in the centralized setting. And the interesting thing here is that there is a market failure because of the rampant speculation, everybody buying up domain names, hoping for the platform to increase in value. All of the useful domain names are gone. And because of that, the platform is now not as useful, right? In turn, preventing the hoped for increase in usefulness and value of the platform. So all of these reasons why the decentralized setting is really hard. And I'll kind of leave it at that. I had some ideas here for how to go about this, but the point is that this is a hard problem. It doesn't work quite well. When we analyze Namecoin, it doesn't work well at all. There are a lot of names that have been registered, but only a tiny, tiny fraction that actually had non-trivial content. It was pretty much a ghost town when we looked at it. My claim is that we still don't know how to design decentralized name markets. A lot of people are trying. Another system called Blockstack is trying. I don't think we have really good solutions in practice today, and we need some really rigorous theory here.
To me, this sounds like market dynamics. I mean, now the price is high, maybe the price will go lower, and eventually Namecoin will become more popular, but I'm not sure this is like something that needs to be handled after the market decides to.
So are you saying why is this a new problem, or?
Why is this considered a problem? I mean, if you price something done by the high price and nobody's buying it, then it's not better.
OK. So running an auction for names, and Matt and I have chatted about this. We don't know an obvious way to do it, and I'm happy to chat offline about that. Yeah. So even if you can theoretically think of a mechanism that you want to employ, doing that in this decentralized setting turns out to be quite non-trivial. So that's one of the barriers. There are a few others. So let me quickly finish up here so that we can go to break, but then I'll stick around for questions. The last thing I wanted to say is that we had another paper where we looked at decentralized order books, how you match bids and asks in a decentralized system. That's another key component of designing these decentralized markets. Again, it's not so straightforward. The argument that we made is that instead of a continuous auction, you have to do a call market. And so that changes a lot of the dynamics of the kind of markets and systems that you would build on top of these things. And then this is the reference to the paper. So that's pretty much all I had for you today. So to summarize, I argued that we might want to consider more realistic models along several lines, such as incorporating non-strategic behavior into game theoretic models of mining. And also, in the second part, the adoption of smart contracts in practice, I think, has given rise to a number of interesting theoretical problems, because smart contracts have some interesting properties. And I gave 3 examples of that. And I think these and many more can lead to interesting theory research questions. All right, thank you very much.